So we'll talk about how to estimate the parameters of a simple linear regression with the help of multivariate calculus. That is, we want to finally be able to derive this result right here. Right. So the way we go about doing this is our simple linear regression problem where y is equal to 1x. This is basically 1x is 1 is a n cross 1 vector, x is a n cross 1 vector, uh, n cross 1, so that is an n dimensional vector. These both of these are n dimensional vectors. B is basically like beta naught beta 1 transpose, so a 2-dimensional vector plus epsilon. Epsilon is again an n cross 1 dimensional vector. So if you match dimensions, this matrix is a n cross 2 dimensional, this is 2 cross 1, so this multiplication is n cross 1 plus n cross 1, and y is also an n cross 1 dimensional vector. So the dimensions, the multiplications of the dimensions do make sense. So this was just a sanity check, and then to perform the computation we'll need to define the error, which we define as s of beta. This is the error, which is defined as the sum of squares of individual errors, which can be written in vector notation as follows, where x, I'm taking x to be the matrix given by concatenating the vectors 1 and x. Both of these are n cross 1 dimensional vectors. So now to be able to find the value of beta hat, that is the optimal value of beta, which gives us the least error, we'll do dou s by dou beta equal to 0. For this we'll use some results from multivariate calculus. So dou by dou beta of this is basically the this expression reduces to this expression right here. You can check. Then dou by dou beta of this quantity right here is 0. Dou by dou beta of this quantity right here is from a result in vector calculus. Dou by dou x of ax is given by a. This is the result we are using here. Right. Now dou by dou beta of x beta whole transpose y, we can write this as this expression right here, and x beta transpose times x beta can be written as this, because we are able to write this because we know a b transpose is equal to b transpose a transpose. Using this result we are able to write this. Then dou by dou beta of this thing, again we have a result from vector calculus, which is dou by dou x of x transpose times a is equal to a transpose. This is a result from vector calculus. Hence we can write dou by dou beta of this thing to be equal to this quantity right here. And another vector result from vector calculus is dou by dou x of x transpose ax can be written as x transpose times a plus a transpose. This is another result from multivariate calculus. So we can write this as this, right? Yeah. Now this quantity is basically, this becomes minus 2y transpose x. This becomes, since x transpose x is a symmetric matrix, this becomes 2 times this thing. Then to find the optimal value of beta, that is beta cap, we need to set d dou s by dou beta to equal to 0. Setting this to 0, we get this expression. Then we get post multiplying by x transpose x inverse, we get the value of beta transpose to be this. Taking the whole transpose of this expression on both LHS and RHS, we get the following. And yeah, and a b transpose is equal to b transpose a transpose, so we get this expression. Now and then we and a b transpose is equal to a transpose b transpose a transpose, we reduce this to this, and now we need to evaluate this expression. Now we know that if a matrix is symmetric, then its inverse is also symmetric. This is the result. Also, x transpose x is always symmetric for any vector x. Using these two results, we know that x transpose x inverse transpose is the same as x transpose x inverse. So finally, beta hat can be written as this quantity right here. Yeah, this is the proof.